Hello, welcome to Guidancee Education channel. We are continuing class 12 physics, chapter 1, charges and fields. The subtopic is Gauss law, its applications. Now let us see the topics that are discussed under this heading. Topics discussed: application of Gauss law, part 3. We have to discuss four topics: electric field due to uniformly charged spherical shell at a point: 1. Outside the shell. 2. Inside the shell. 3. On the surface of the shell. This topic will be of great use to you. It is a very important topic for examination. So watch the video completely without skipping. And if you think the video is useful, do like the video, share the video, and also leave your comments in the comment box below. Click the I button in order to watch the other parts in the series. Do not miss the questions given in the description box below. If you have not subscribed my channel, do subscribe it now and also press the bell button so that you get intimated as soon as new videos are posted. Thank you very much for your support. Come, let us start the class. We will derive an equation to calculate electric field due to a uniformly charged shell at a point outside the shell. The point where we want to calculate the electric field is at a distance, say r, from the center of the shell. I have marked several such points on the diagram: P1, P2, P3, P4, P5, P6, etc. All these points are having the same distance from the surface of the uniformly charged spherical shell. In the diagram I have given here, the spherical shell looks like a ring, but actually in 3D it is in the form of a sphere, like a ball. Charge is all over the surface. The red dotted surface is the Gaussian surface. It includes the charged shell. This is the distance of the point from the charged shell. So when we consider the center of the shell, from the center of the shell, it is at a distance small r. The Gaussian surface also is a sphere. Small r is the radius of the Gaussian surface. It is also the distance of the point where we want to find the electric field, considering the center of the shell. We have to derive the equation for electric field using Gauss law. Gauss law is, again, I remind you, is for flux. So the general formula for flux using Coulomb's law is equal to E dot ds. When we are applying Gauss law, we have to consider a Gaussian surface. A spherical Gaussian surface is chosen. Electric flux on all these points located on the Gaussian surface will be the same. Hence, the electric field also will be same. For the purpose of further explanation, I will add a point P7 at this point where I have marked small r from the center of the shell. You might wonder why we are considering this small r distance rather than the distance of the point from the shell. You will automatically understand that when we finish the derivation. As the shell is positively charged, the electric field is radially outward. So at point P7 also it is radiating outward. That is the direction of the electric field. When we consider a small area element at that point, the area vector also will be in the same direction, that is parallel to electric field. So coming to the derivation, flux is equal to E dot ds becomes equal to E ds cos theta. Theta is equal to 0 here, so it becomes E ds. Integrating for all the area elements on the surface, we get it is equal to E integrating ds, which is equal to E. Yes, the surface is a sphere. So we have to substitute for the area of a sphere. So it becomes equal to E 4 pi small r square. So flux is equal to E 4 pi r square. Applying Coulomb's law. As per Gauss law, flux is equal to Q by epsilon naught. For surface charge distribution, Q is equal to sigma, the surface charge density, into area. Here area is 4 pi r square. Here r is the radius of the sphere. So 4 pi capital R square. In the case of a plane sheet, we have already seen that it is independent of distance. If you have not yet watched that video, click the I button in order to watch that. Q is equal to sigma 4 pi r square. So this equation will become sigma 4 pi capital R square by epsilon naught. Now we have two formulae, the left hand side of which is same. So we can equate the right hand side. Okay. So E 4 pi small r square is equal to sigma 4 pi capital R square by epsilon naught. From this, E is equal to Q, because sigma 4 pi r square is equal to Q divided by 4 pi small r square into epsilon naught. So electric field outside the uniformly charged shell is given by the formula. I will rearrange this. E is equal to Q by 4 pi epsilon naught r square. You have to understand a few more things related to this. Let us see one by one. This equation is familiar to you. So this is the equation for calculating electric field at a point at a distance of small r due to a point charge located at the center. So it is assumed that all the charges on the surface of the spherical shell is concentrated at the center of the shell. That is why we considered the distance of the location where we want to find the electric field as small r rather than its distance from the surface of the shell. I hope your doubt is cleared. Q is the magnitude of the charge. So from this we can assume that for a point outside the shell behaves in such a manner that all its charge which is present on the surface is concentrated inside the shell, that is at the center of the shell. So that is one concept that you get. I hope this is quite clear. Now let us recall the equation that we obtained for a plane sheet and then compare that with the equation that we derived just now. For the plane sheet, electric field is independent of the distance, whereas in this equation you find the distance small r, which is radius of the shell plus distance of the point from the surface of the shell in the denominator. So electric field is inversely proportional to square of the distance r. So that is one remarkable thing that you have to notice. Okay. In this case, small r, that is the distance of the point where we want to find the electric field, is greater than capital R, that is the radius of the charged sphere. Okay. Now we will pass on to the next topic. Now let us see electric field inside a uniformly charged shell. What does it mean? Distance of the point small r is less than the radius of the shell capital R. This is the uniformly charged shell. The point is inside the shell. I have shown several points which are all equidistant from the inner surface of the shell. The distance of these points from the center of the shell is small r. The radius of the shell is capital R. Applying Coulomb's law, electric field is equal to E dot ds, that is for each area element will be equal to E ds. For the whole surface we have to integrate all the area element in the surface. Integrating, we get E integrating ds equal to Es. When we consider this whole spherical area, not circular, spherical area, then it becomes equal to E 4 pi small r square as per Coulomb's law. Now let us apply Gauss law. Flux is equal to Q by epsilon naught. Q is the charge enclosed by the Gaussian surface. The surface does not enclose any charge. All the charge is outside the surface, that is on the surface of the shell. So Q is equal to 0. So this becomes flux is equal to 0. That is one formula. Here you have flux is equal to E 4 pi r square. Equating the two, we get E 4 pi r square is equal to 0. And from this you can write E is equal to 0. So what is the conclusion? Electric field inside a shell is equal to 0. For a point outside the shell, R is greater than radius of the shell. Now we will pass on to electric field on the surface of the uniformly charged shell. Okay. R is the radius of the sphere. The point is on the surface of the sphere. Small r is equal to capital R. So we will use only capital R. As per Coulomb's law, flux is equal to E dot ds. It is equal to E ds here. This is flux for a small area element ds. The surface has so many such area elements. So we have to consider all that. So we have to integrate. So integrating, you get E integrating ds. Integrating ds is equal to s. So this becomes es. Substituting for the whole surface, you get flux is equal to E 4 pi r square, because small r is equal to capital R. As per Gauss law, flux is equal to Q by epsilon naught. You have two equations here. We equate the right hand side. E 4 pi capital R square is equal to Q by epsilon naught. From this we get the value of E. E is equal to Q by 4 pi r square into epsilon naught. We just rearrange that. 4 pi epsilon naught into r square. So this is the expression for electric field at a point on the surface of the uniformly charged shell. Compare the three cases that we have seen. Number 1, electric field at a point outside the shell, Q by 4 pi epsilon naught small r square. We will rearrange this. 1 by 4 pi epsilon naught Q by small r square. Here the distance of the point small r is greater than the radius of the sphere capital R. Second case, electric field inside shell, that is equal to 0. Small r is less than capital R. The third case, electric field on the surface of the charged shell. That was what we did just now. 1 by 4 pi epsilon naught Q by capital R square. You should be very careful with this R. Here small r is equal to capital R. Small r in the first case is greater than capital R. So the value of electric field outside the charged shell will be less than the electric field on the surface of the shell, because the magnitude of capital R, that is the distance of the point on the surface, is much less than small r in the first case. So maximum electric field is on the surface of the charged shell. Now let us represent this in the form of a graph. This is y-axis and this is x-axis. This is the origin. Electric field is taken along the y-axis and distance small r is taken along the x-axis. From 0 it goes on increasing and reaches a distance equal to capital R, that is surface of the shell. 0 is at the center of the shell. For this portion between 0 and r, small r is less than capital R. That is, distance of the point is less than radius of the shell. For that we have the expression electric field inside, that is inside the shell, is equal to 0. So for this point, it will be on the x-axis. On the surface, electric field is maximum. What is the expression? 1 by 4 pi epsilon naught Q by capital R square. That is the value. This point has this value of electric field on the surface. After this point, when distance of the point increases, electric field goes on decreasing. I hope these points are quite clear. There is no need for any confusion. There is no need for any fear either. These points are very simple. At the same time, they are all very important for examination. I hope I made it quite clear. If you think the video was of use to you, please like the video, share the video, and if you have any doubts, please leave them in the comment box below. If you have not subscribed my channel, do subscribe it now and also press the bell button for notification of new videos. Thank you very much for your support. We will meet in the next video with another important topic like this. Till then, bye.